Hello. Thank you so much for the invitation, first of all, and to give me the possibility to talk to you today about how we are exploiting quantum effects for low temperature scanning, magnetometry, and current sensing. And I'll start with something slightly different, namely what I call here the human history of failure analysis, specifically of human failure analysis. So 500 years ago, if there was a failure in a human body, typically to analyze it, you had to wait until it's a fatal failure. And there were rather volatile methods, not volatile, but destructive methods to see where that problem actually sits and how and whether you can localize and analyze it. So 500 years later, which is nowadays, we have techniques like MRI, and you have an in vivo and non-destructive way to analyze failures. And not only that, if you think about what MRI enabled us, pharmaceuticals, you are able to understand how the brain works and so on. So now, from our perspective, it makes perfect sense how we got there, and that an application like MRI is perfectly sensible. But for other technical areas where failure analysis is really needed, like for instance electronics that only work at cryogenic temperatures, we don't have such a measurement modality until today. So we thought of developing such a sensor, such a product where you as a customer can come and enter your device, enter your sample, and measure at the nanoscale magnetic fields from room temperature down to 2 Kelvin. And why do we think this is interesting? Why do we think that there's a market? So I already mentioned cryogenic electronics, and I'm not only referring to superconducting qubits. I'm also referring to literally cryogenic electronics, and because of or thanks to superconducting qubits, there's more and more research going into having electronics like DACs, analog to digital converters, and so on, in a cryostat, and that boosts efficiency in a very significant way. But you need to have some sort of tool to analyze whether your design circuitry really works as it's supposed to work. There's another aspect of research where magnetic field sensors are needed. So here, these two images here show, or illustrate and show actual skyrmions. So skyrmions are, in some sense, quantum quasi-particles that can be used for information storage, or that are thought to be useful for information storage. So these typically work at room temperature, but are also really useful at lower temperatures. Not like millikelvin, but maybe 100 Kelvin. And here also you need a sensor and a way to manipulate these skyrmions on a nanoscale. And finally, something that probably was mentioned, or that people here use quite often, are superconducting nanowires for single photon detection. So the way this works is you have this meandering nanowire, which is superconductive at low temperatures. A photon comes and breaks the superconductivity. So this is how it's supposed to work. However, if the device has an issue, or there's a leakage, or the superconductivity is not as directed as you would like, to have it, you throw the device away, and you don't even know if the way you thought it's designed is reflected in reality. Again, a use case where a scanning magnetometer would be rather beneficial. So I try to delineate some use cases where quantum magnetometry at low temperatures is useful. So now let me assess, or let me count the requirements for such a technology. So I already mentioned a couple of times, you need to have a sensor that is able to resolve magnetic fields or currents down to the nanoscale. You should be able to go really from room temperature to a few Kelvin. I talked mostly about few Kelvin, but also mentioned there's a trend towards higher temperatures. There are high temperature superconductors, so you don't want to limit yourself to only 2 Kelvin. And finally, you want to be quantitative, obviously, but especially also non-invasive. So you don't want to change your typically rather delicate system with your application, with your sensor. And so there are, for some of these aspects, for some of these requirements, there are solutions. So you have a magneto-optical Kerr effect microscopy, for instance, but that is typically limited to optics resolution, to the radial limit, like let's say 400 or 500 nanometers. You have scanning squids, they only work at low temperatures. You have magnetic force microscopy, which is an AFM that is magnetic, and you don't really know what happens to your device or to your sample once you probed it with a magnetic probe. And we believe that a solution, and a well-proven solution, is the nitrogen vacancy center in diamond. So the way this works is basically you have a nitrogen vacancy center, which is typically implanted in a synthetic diamond. And it works like you can think of it as an artificial atom. So this artificial atom is sensitive to magnetic fields. And the way you ask the envy center how strong the magnetic field is by means of illuminating, exciting it with a laser, and you are measuring the fluorescence at the same time. While you're doing it, you have a radio frequency, a microwave source close by, and you're changing the frequency of that microwave source. And at some point, the fluorescence will break down. And if you keep track of the frequency where the loss in fluorescence occurs, you know exactly by fundamental physical constants how strong or how weak the magnetic field is that the envy center experiences. So it's quantitative, and it's also calibrated by nature, basically. So you don't need to go and calibrate your sensor. And some credit to previous developments. The first publication that showed a scanning magnetometry by the means that I just outlined is 2008, and people used an atomic force microscope, a tip, an AFM tip, and attached to the tip a nanodiamond. And in the nanodiamond, you had an envy center or multiple envy centers, and then you ran over your sample. So in this publication, actually, they used a hard disk as a sample. And while this proves the technology, it is very bold, and it would be even more bold to say we're going to sell something like this, and we're going to have the customer attach a nanodiamond to a very, very tiny tip. Forget about it. A few years later, 2016, this was realized also in a cryostat. So cryostats are notoriously difficult to operate. You have confined space, you have vibrations, and so on. And also people realized that instead of attaching a nanodiamond to a tip, to an AFM needle, you can just make the tip of diamond and implant an envy center in it. So that renders things much more robust and much easier to use. And finally, to kind of delineate how cold you can get with such a sensor, 2022, this was proven in a millikelvin in a dilution refrigerator. So this is what we made out of it. This is our demonstrator. This is sold, installed, and operational since March this year. We kickstarted the development by funding that we received from Asterix, which is a EU quantum flagship. So what you see here is, so there are two electronic rack units with all the control and analyzers that you need. You have closed cycle cryostat, which means once it's cold, you don't need to refill helium or anything. And on top of that, you have an optics platform that comprises everything from a camera, confocal microscope, lasers, and so on. Now, you might ask, well, so we saw this proof of principle, 2008, so it's more than one decade old, and we think it's rather obvious that there are applications for it. So why did it take so long? The reason why it took so long is because of the complexity of it. We have at least 5 topics to address, which is the atomic force microscopy. So we're talking about the interaction between the diamond tip and the sample. And while AFM is a technology that is, or method that is known since more than 1 decade, the exact behavior, the interaction between the diamond tip and the sample is quite different from typical AFM methods and need to be understood for robust operation. The optics are important, especially the drift freeness of the optics, because the measurement can take up to several hours depending on the image, the resolution, the scan area of interest. So you want to be you want to be able, you want to make sure that you collect all the fluorescence from your NV center. And when I say drift freeness, I'm talking about something like 50 nanometer that we allow the whole beam to drift over several hours. Software is of course key, because that's what the user is interfacing with, and it needs to be easy to understand. It needs to be able to analyze the sample on the fly. You have the cryostat, which is mostly an engineering issue because you have space constraints, and you have the optically detected magnetic resonance, ODMR, which is also somewhat of an engineering challenge in a cryostat, because you need to cram in even more wires. You need to have coaxial cables capable of delivering microwave frequencies to your sample. It needs to be flexible at cryogenics. It needs to be vacuum compatible, and it needs to be non-magnetic. So, some results. So this instrument, or specifically the NV center technology, is done by and in collaboration with Q2B. And you can see here it's probably hard to see. So this one here, that's the diamond pedestal, and the needle itself you can't even see. So the diamond pedestal, and inside the diamond you have the NV center, is hanging on this prong here, and that's a tuning fork, which provides you with the fact that you can use it as an AFM. This large object here in the background, that's the microwave antenna, and both tuning fork and microwave antenna are fixed on one PCB. So that enables us to be alignment free. So you don't need to align your microwave antenna to the NV center, and that's a huge benefit, especially when you work at different temperatures. So here you can see the magnetic field sensitivity for continuous wave for CW ODMR. That's the most standard protocol that you can run. And at 3 Kelvin, you achieve around about 3 microtesla per square root hertz. So here's the data. I just ran this for like 2,500 times, sampling time 1 second each pixel. So that's how I got there. And maybe more for the experts, the NV center is so sensitive that we can actually observe the hyperfine splitting, which is the interaction between the free electron of the NV center with a nearby N15 isotope. So for proving that we have a sufficient resolution of the magnetic field, I used a skyrmium sample here. I did a 2x2 micrometer scan. The reason why I use a skyrmium sample, it's a great benchmarking sample. It has a reasonably fine magnetic structure, and it's rather robust. So in the cross section here shows that from a larger to a from a small to a larger magnetic field, this is around about 60 nanometers, and that matches pretty accurately what we expect here to be able to achieve in terms of magnetic field resolution because this was measured 50 nanometer above the sample. So the diamond tip was not in contact, but it was 50 nanometer above the sample. And to a very good approximation, the distance tells you the magnetic field resolution that you can theoretically achieve. Right. So now on current sensing, so well, magnetic fields and currents are somewhat intimately related to each other. And our colleagues from Q2B showed here first at room temperature that you can image and resolve current flows down to 30 nanometers with that exact technology. So what they used here is a circuitry, and they traced basically the current flow through this meandering electronic device. And what's really important here is to show that you can achieve a resolution of like 30 nanometer, because especially for front end of line devices, you need to go there. You need to have such a resolution. Right. One disadvantage of scanning magnetometry is the speed, is the acquisition time, because well, it's a needle that you scan over your device. So there's no single shot measurement. You do it pixel by pixel. Now, if you want to measure faster, and you can sacrifice the magnetic field resolution, the spatial resolution, you can do something different. We call it NV wide field microscopy. And so instead of having a pillar of diamond and a single NV center, you just use a slab of diamond with many NV centers inside. You put it on your sample, you illuminate it homogeneously with a laser, and with a very sensitive CCD, you get a single shot and an image that spans as much as your field of view allows. And you can get what 50 by 50, 100 by 100 microns, micrometer image in a few seconds, and can learn about current flows or magnetic fields. And this has been proven also some years ago already. So we thought this is a very natural way to go, and we wanted to go there, and we did go there. So this is our development, which we are going to install next week at the customer side. So unfortunately, because we haven't installed it and agreed with the customer on what to publish, I can't show you the result of what this thing here is capable of. I can tell you the equipment, some of the technical features. So the cryostat looks very similar to what I've shown you on the previous slides. It's a bit more compact because you're not so sensitive on vibrations anymore. The cooling power is a bit better because you have less stuff down there in the cold space. Also, you need a bit less electronics because you don't need to control this diamond needle above your sample. Optics are more complicated because you have a very sensitive camera, you have a smoke detector, and lots of electronics, so you can send in high-frequency signals. And yeah, that's an illustration of the device, and the green space here illustrates where the sample is sitting, or where the microscope is inserted. So yeah, I'd like to thank you for your attention. And yeah, that's two of my colleagues, and we developed this instrument at attocube. And here's a photo of the colleagues from Q2B. Thank you again.